So actually, there's a couple of things, and this morning you can see my console had a lot of problems installing installing Ken's package. So maybe you guys can take a couple of moments to yourself to. There's a part of the lecture. I don't know if you guys have looked. Sorry, this is not right. Of course, there's a part of the lecture where you actually need to install his package, and it's not easy, right? So that is, I think it's here. But you will see that to install his SMMR package, you actually need to install DevTools first. And the thing is, it's not necessarily very easy, right? So let me see. I'm going to point it out to you before I start this because I think it's important just to practice to see if you can do it. Especially, I think your midterm is actually is online. But he may ask you to do things like, I know for sure he's going to ask you about the sign test and the median, and even the median test, even though you're learning median tests today, which means that you have to know you have to install these packages. It's not going to be excusable if on your exam you say, I could not install the package. It's right. He'll just say, well, I gave you guys this thing weeks ago, right? This should have been installed. So I want to find the slide where I installed it so I can show you guys how to. Just give me a second. I don't know why I can't find it. This is really annoying. Let me see. Maybe I'll just, I had it before. It's so weird. I'm sorry. I'm gonna just see if I can use. Maybe I'll find it in lecture notes. Yeah. So you can see that. I cannot for life may find. Anyways, it's in one of his lectures. It is in this week's lecture. So have a look and see. I truly cannot find it right now. So whenever you want to find something, you never find it. Yeah, here it is. This is it, right? So you see that in order to use this package as MMR, you have to download DevTools first. But sometimes there's issues installing DevTools and then using install GitHub. It's because you need to use install GitHub, and install GitHub is in the DevTools package. Right, because his package as MMR is actually not in CRAN, it's in GitHub, it's on his GitHub page, right? So in order to install his package, you need to first install DevTools. Please check, because it will not be an excuse in your exam when the sign test comes up, and it will come up, and you have not installed the package, right? So if you fumble on the exam to install this package, you've lost time and you're not going to get it back, even if you tell them, oh, I had problems installing my package, right? Because there's no assignment this week. Do the midterm, which means that you may think to install the package at the last minute, which would be a very big mistake. So don't do that. Install it early so you know that it works, and go through the examples to make sure you're not behind for the exam. Okay, now I'm going to go over some things I think are important. How many of you have heard about qqplots before? So you guys have probably took, everyone took your BP7, but some of you may have taken C67, which is regression analysis. And if you did take C67, you probably saw the qqplots, but if you did not, you would not have seen it. So has anyone here heard of the qqplots? It's totally fine if you haven't, but I just want to know how much detail to go into, because it's definitely on your exam. So I want to know how much detail to go into. So if you haven't heard of it before this class, let me know. And I'll just go over a quick lesson to explain what it's doing so that you don't memorize it for the exam. So show of hands, just put in the chat, yes, no. How many of you have heard of qqplot before this course? Yeah. It's one method to check for normality, exactly. It's one method, but there's a reason why that's the way, right? So that's exactly it. It's a method for determining normality, Eddie. But you can see that if you look at what it's actually, so the qqplot looks like this. I should grab my stylus pen. Anyways, it looks like a scatter plot of the residuals. No, not the residuals. The theoretical quantiles against the residuals of your thing, right? So, or your values of X. The theoretical quantiles are actually the quantiles for the normal distributions. So you guys know that it's normal with a mean of 0 and a variance of 1, right? So these are theoretical quantiles for normal distribution with a mean of 0 and a variance of 1, right? On the x-axis. Now, if your actual data, or sometimes this is data, if your actual data is normal, then what should happen? What should happen is that when you look at the linear line between, so you'll have a linear line that looks like this, right? The extent to which your actual points turn the line will tell you it's a truly normal relationship, because there'd be a one-to-one map between your theoretical quantiles and your residuals. Maybe the map is the following. Your data Y is equal to some slope term of the residuals, plus B. If there's really a linear line, if there's truly a linear relationship, as in your data is actually normal, then there should be a one-to-one relationship between your theoretical quantiles and your data. That's because if your data is distributed normal with the mean mu and a variance of sigma squared, you should be able to transform it to a standard normal by shifting by the mean. So you take your actual mean, be it, X bar, your true mean is mu, and you would actually shift your data by a factor of mu, right? So the z-score allows you to do that transformation. So I'll just show you what it is. Right, so z-score is actually equal to your data minus the mean divided by sigma. So you can see that you can transform your data that is y into something that is z by this transformation here that you see here, right? Which means that if your data is actually truly normal, then when you put it in this z-score, there should be a one-to-one map, which is this is the linear relationship here, because this is a linear translation between your theoretical quantiles and your residuals. Because you can see this is linear. This is a linear map, basically, right? You can express this in this form here. But if it's not true, if your data actually truly is not normal, you would see that instead of your line trending like this. So the theoretical so do any of you know about, so the quantiles, so the normal distribution looks like the following, right? So quantiles look like the following. Something that's distributed normal, right? Centered around 0, and this goes between 3 to -3. These are quantiles, right? Quantiles are percentiles. Like when the quantile for, let's say, the median is that is equal to 0. 0 is the median because you can see that half the data is below 0 and half is above 0. So the quantiles are actually percentiles. It's like how many observations fall below your data or above your data, right? So that's what quantiles happens to be. That's on the x-axis. So if your data is actually normal, you should be able to find a correspondence between your actual theoretical quantiles and your data, because you should be able to transform your data into something that's on this distribution. So through this transformation here, Eddie, you should be able to transform your data that is normal through this transformation that's linear onto this map here, on this distribution. Do you understand? Like because that y is normal, there's a linear map that transforms y to z, and it's given by this basically. Which means that any y should be able to should be transformed onto this map here, on this distribution of quantiles, basically, that spans between -3 to 3, where 0 is the median. If your data is not actually normal, what happens is that instead of sitting like this, in a linear kind of thing, where there's a one-to-one map that is given by the z distribution, the z thing here, you get things that look skewed, right? So you can actually determine if your distribution is left skewed or right skewed by the way in which your data doesn't address the line. Right, so you'll actually see in Can's actually knows when your data does the following. Let's suppose your data does this instead, right? Where it's truly actually off the line, like it does this. It's truly off the actual line. This is right skewed. And if instead your data does the following, where it's falling below the line, maybe it's doing this here. This would be considered left skewed, right? You can see that in neither so this is left skewed. In either scenario, it doesn't actually trend the line. There's also something called long tails, which I actually will show you. There's something when you have long tails where it actually is the following. So there's a couple of things that can go wrong. There's also something that looks like this, where they trend the line, but then they do this. Right, so this blue line here, this would be considered a T distribution, where you can see it trends the line in the middle, but then the tails are kind of long. This is T distribution. So there's 3 scenarios where your graph would reveal that it's not actually normal. And he will ask you this in the test because he wants to determine if you should use the actual t-test. Right? So the t-test you cannot use if your data is not actually symmetric or normal. You have to use something else. That's what the sign test is for. The sign test is used. The sign test and the median test, guys, are things you use for data that's skewed, right? Or has long tails. If your data is heavily skewed, you probably should not use the t-test, because it's the t is, remember, it's given to it the following. It's your observation minus mu over s divided by root. And so you can see that implicitly this y is distributed normal. So it's assuming some kind of normal distribution or normal structure to your data. If your qqplot does not reveal a normal structure, you actually can't use the t-test, because you can see that this y bar is distributed normal, and this is a chi, like I said last week. S is distributed chi. A y bar is distributed normal. The ratio of normal to chi is t. So if your actual data is not normal, you should not use the t-test, which is why he introduced the sign test, right? So that's really the point, right? So I'm going to show you guys what to look for in the plots. Then I'm going to go over how to do the sign task when you have, or how to recognize to use to do like how to recognize to use the sign task when you have skewed data. So I keep using empty card just because it's kind of, you know, like familiar to me, or I don't know. Anyways, I'm gonna download it. So first of all, if you can see, if I just actually show this, right, you'll see that if I just run this part here, I'm gonna block this out. You'll see that you get this. The reason why I draw the line is because, and this is in base R, by the way. So I'm showing you base R just because like we shouldn't, this is how you do it in base R. Please don't use this for your exams. This is base R. Do not use for exam. You know, use tidyverse, which I'm going to show you in a little bit below, but this is how we used to do it before we had tidyverse packages. You can see that you actually don't know if, I mean, you can kind of suspect it might be normal, sort of, but not really, because you don't have the line on your data points. You have to put the line on the data points to actually see what the structure looks like. So that's QQ line basically, right? You see that I put the variable weight, right? And then I put, so that you have to specify what variable you're looking at basically. So I put weight. Anyways, if you run it, you get this line here. You can see that it's sort of normal, but it has some problems over here, right? You might have some suspicious outliers, and obviously we know that outliers can shift our mean, so it might be something we need to be a bit careful of, basically, right? But let's kind of hold this thought. I'm going to sample from a random variable I know is normal, right? So I'm going to set the seed. You can set the seed to whatever you want when I post the lecture notes. I'm going to show you how to use tidyverse, right? So you can see that you should not use the first code I gave you, right, on the task, because it was just me playing around. You really should actually use tidyverse, which is, you know, how we're doing things in the course. So using built-in functions for base R wouldn't necessarily be appropriate, right? So be mindful of this. Anyways, I'm going to run the library tidyverse. I'm going to set my seed to this. Now, this is a random, so you can see that in general, if you look at the R norm, it actually will give you, you can see you're supposed to specify a sample size of -32 with a mean of whatever you want. The default is actually to do mean of 0 and standard deviation of like 1. So if you don't specify a mean and standard deviation, it's assuming that it's 0, 1. But I don't want that. I picked 2 and 1, right? So I really should, I picked a mean of 2 and a variance of 1. Probably I should have picked 3 because the actual mean for weight is 3. So if I look at the mean of weight, like 3, right? So probably I should change to 3. Anyways, let's run that and see what we get. I remember when you want to use the ggplot, you have to you cannot give it a vector. If I don't change the vector to a data frame or like a tibble, I can't actually use ggplot, right? So that's the thing. So I need to change to a data frame so I can put it into the qqplot function. If I don't, it won't actually run. You have to give it a data frame, right? So I'm going to create the tibble. Now you can see that if I look at what this happens to show me, it's actually a data frame, right? It's a data frame with only one column basically, right? So I want to see if there's something here, and you can see the length of this thing should be, oh, sorry, the length of, see, oh, that's not right. So table and data frame are similar, Eddie. The only difference is that, so if I look at Z, let me see for a second, because it should have given me, yeah, you can see that it's true that it's a data frame basically. So if I look at the dimension of Z, you can see that it's a 32 by 1 data frame. But so the difference between a table and a data frame is that when you want, they do the same thing. This is a data frame right now, but the reason why I might use tibble sometimes is if I want to look at tables, right? So tibble allows me to create tables, right? So I can use a table function. So this table function here, if I want to look at characteristics of my thing, I can do it on tibble. You see it's giving me characteristic function. So I can use, so yeah, if you want to use table function to look at the characteristics of your data, you probably wouldn't do it here because these are just numerical values. But if you have something quantitative, you want something categorical you want to look at, right? So just like Y tibble and not data frame. If I, want to, let's say, create a table of my categorical data. Tibble allows us to do this, to partition a variable based on the features, right? Based on the levels of a variable. So for instance, let's suppose your tibble was just actually a 2 by 32. So just had, it had like BB, it had like, let's say, you know, so example, a table of, let's say, table of employed, yes, no. And voting party, let's say liberal, conservative, NDP. If you wanted to create, if you wanted to create like a 3 by 2 table or something, wanted to create, let's say a 2 by 3, two rows and 3 columns. You can do table of the, you can do table of table. Whereas you cannot do that for the data frame, basically, right? That's really the difference. So they function the same, except when you want to actually look at, you want to stratify based on certain things, then you might want to use table. Does that make sense? So essentially, they are really both data frames, except when, depending on what you want to do. And so you cannot do table of data frame, basically. Sorry, you cannot do table of data frame. It's not really, it's not really a thing, right? So if I put table of, let's say, empty cars, doesn't make sense, basically. You can't do it, but you can do table, basically, table, right? This is why, so sometimes when you want to create a table that would do, let's say you want to create a 2 by 2 table, and you can do that with table. You can't do a data frame. Okay, so that's really the main difference. But for the purpose of this course, you probably won't be using tables anyways. They probably have the same role in this course. Okay, so now you can see that the distinction between like what you've done before and the qqplot is now you're using STAT33. Right, and then you can see how the reason why I showed you how to do it in base R is because when you want to add features to tidyverse, it's kind of similar to how you do it in base R, because you can see here QQ norm doesn't run the line unless you ask it to. Similarly, you don't get the line for the data unless you ask for it, right? So you have to add stat QQ line if you want to actually see it. If you run it, we get the following. It looks like this, right? So you can see that this is a normal data. I know it's normal because I sampled it that way. That's why for the most part, the line, the data points trend the line. That's not going to be true for data that's not actually normal. So you can see for the most part, you can see the points that trend the line for the reason I gave you. The theoretical quantiles, there's a one-to-one map between that and the data. But sometimes it's not true, right? And you have to be mindful of that. So if he gives you, when it says, look at the QQ plot, does it make sense to use a t distribution for this data? You might say no, right? So I'm going to give an example here. R gamma, has anyone seen the gamma distribution before? It looks kind of like this. It's a right, actually, you all have seen it, I guess, right? Because everybody here saw 57, but gamma is a right skewed thing. It looks kind of like this, right? It's right skewed. So I already know I'm drawing from random variable. It is right skewed. If I run the seed, let's see what I get. I can actually show you the histogram, right? So I'm going to just run this. Before I create a table, I'm going to actually show you what the histogram looks like of the data. So let's do GG. So let's do histogram of Y. You'll see that, oh, my margins are too wide. I'm going to do it here. You will see that if you run this, I'm going to put it here. You'll see it looks like this. This is obviously right skewed. This is nowhere near symmetric, right? So we definitely cannot, I could have used ggplot, but things I can't use ggplot. The reason why I use base R at this point here is because I have not created a tibble. So because I didn't create a tibble, I cannot put the vector into ggplot and get it to run. That's why I use base R. You can see that this vector is not symmetric because it necessarily so because I sampled something I knew was right skewed. Right, but now let's see what happens if you look at the QQ plot. So I'm going to make a note here so that when you look back again, you're not confused. I used histogram instead of ggplot. Use base R because at this stage I had no data frame. I had no data frame to give ggplot. You cannot run this without a data frame, right? Okay, so now let's actually create a data frame. Oh, I should have actually. So now let's actually create a data frame. create a data frame. Okay, let's create one. Okay, so now it's a data frame. Let's check. There you go. Now let's put this y into the thing. So this might be confusing to you because you can see my variable and my data frame are both called y. But anyways, you can see what I'm doing here. I feed it y. The samples, the data is also called y. You can see that in the data frame y, the variable is called y. Now I should run this. You'll see that. What do you notice here, guys? What do you see in this graph? What's problematic here? What do you see on this graph? Yeah, and you can see that not only is it not normal, in fact, when it's not normal, because when you transform your variable y, so you can still do the transformation based on this thing here, right? You can still do this with your skewed data, but the problem is all it does is shift a right skewed data to something that's still right skewed. It doesn't change the skew of your data just because you did this transformation. So once you do the transformation, the points on the on the normal distribution are still not symmetric. So once you do the transformation using this thing here, because your data is actually right skewed, you'll see that the transformation yields something that is still right skewed and not trending the line, because there truly is no one-to-one correspondence between a right skewed thing and something that is normal. So you can see that it did not actually trend the line up, right, because it's not actually something that's symmetric. But more to the point, you can see it looks like what I showed you here, where it's kind of going off like this to the right. That's how you know it's right skewed, and you actually cannot use t-test here, right? So, because like I said, the t-distribution kind of is assuming that y bar is normal, but it's skewed in this example here because I sampled in that way, right? So you would not be able to use a t-test. You need to use a sign test. He will definitely ask you on the test. He won't even tell you what test to use. He'll just perform a test probably, and if you perform the t-test, it's wrong, right? So be mindful of these things. Because if I were the instructor, I would not say perform the t-test, I would say perform a test. And if your test was wrong, the whole thing is wrong, basically, right? There's no part marks for an incorrect first step that results in a completely wrong conclusion, right? So be careful about this kind of thing. Okay, so now let's look at the t-distribution, because it almost looks kind of similar to normal, except it has long tails, and I want to show you that too. Is that right skewed? Since, yeah, you can see that, yeah, that's true. You can see that all the points are high. In fact, they're so high, they're falling off the line, right? Because the normal distribution says that the normal distribution is like kind of like this, where it's sort of saying, okay, it's saying that the following is true. It's saying your data is like this, maybe, but it should not go beyond, let's say this. But you see you have points that are going all the way over here that is not reflected. That should not have been true for standard normal. The tapers off at 3, but you have these big outliers that are going well beyond 3. So you see that's why it falls off the line, basically, because the normal distribution doesn't really recognize points, or it doesn't have point mass beyond like 3. You can see the normal distribution doesn't have mass beyond 3. I should say density, not point mass, because point mass for discrete things, it doesn't have density beyond 3, right? It just looks like it just has probability of like 0 beyond 3. You can see here. And so, like, if you put a right skewed thing on it, it will just go beyond the line, because it doesn't recognize points like out here, basically. That's why it's confused. Okay, so now let's look at something that's t, because in some way the t-distribution has the same problem. The t-distribution also has long tails, except it has them everywhere, right? So the t-distribution kind of looks like this. So if I have a standard normal, it looks something like this. The t-distribution actually looks kind of like this. It does like that. You can see that it has long tails. So it also has problems. It's still symmetric. We'll center around 0, but the tails are kind of long. And you will see that reflected on both the left and side, at both the bottom and the top of your graph. So let's see. Let's create a new one where I'm pulling something that is actually disputed t. So if I set the seed, I keep putting the same seed. You guys can know I'm kind of predictable at this point. You can choose whatever seed you want. So RT is a random variable with distribution t. I'm just going to say that in general, if you look at RT, you'll see that you have to give a sample size and degrees of freedom. So that's why I said 32 is sample size, degrees of freedom is, let's say, 31. So degrees of freedom for t distribution is always n-1, right? So degrees of freedom is n-1. That's why it's 32, 31, right? So let's run this. And just to show you what it looks like, I'm going to, before I actually do use base R, as I have no data frame yet, I'm going to show you histogram of W. You'll see that it looks kind of a bit symmetric, but different. There's a twist, right? So actually, it's because the sample size is small, you can't see it. Let me actually create a random variable that really is very large in sample size and show you what you got, basically. How to kind of send the margin. So let's do this. And we'll see if this works. Yeah, you can see here that while it's centered at 0, the tails are kind of long. It looks compressed, right? Where you can see the normal distribution has a mode that's kind of compressed, that's kind of peaking really high around between 0 and 1. It's compressed here. It's compressed like this because it's flattening out the distribution to accommodate the long tails. Whereas if I did a histogram of, let's say, R norm with the same sample size, right, it would look different, right? So you can see that the mode is higher, basically. It's because it puts mass closer to 0, 1, whereas the t-distribution spreads it out more. So you can imagine the QQ plot can't look the exact same, right? Because of this. So let's see what it looks like. It looks something like, oh no, where's my plot? Yeah, it looks like this. Notice that while it's certainly true that in the middle, it kind of follows a line because in the middle, it's symmetric, like just like the normal distribution, you see how it falls off the line at the tails, basically. This is very classic of things that are distributed T, right? So it does fall off the line at the tails, right? So the T distribution, the T test does perform okay. No, long tails, it has long tails. Notice that you see that it's, instead of following the lines like this, it kind of keeps extending beyond the thing. And I can make it even more clear if I make the sample size 1,000. You'll see that it kind of has really long tails where it's falling off the line. So if I make this 1,000, you'll see something really strange happen. See? You see that while it trends the line amazingly in the middle, you can't see the entire plot, but it actually fell off the plot. You see it's going to keep extending past this point here. It keeps descending down here. Oh, actually, no, not quite. Does anyone know why it looks, so what happened here? This is actually a good exercise. What happened here for large samples? You see that it actually looks pretty good at large samples. What happened here? I made an error here. What happened at large samples? Anyone know what happened? So it actually looks pretty normal for large samples, right? But not for small ones. Anyone know why? So what happened for large samples? It actually truly looks normal for large samples. How come? So this is something called the central limit theorem. Has anyone heard of the central limit theorem before? Yeah, you can. It's totally fine if you haven't. But the central limit theorem says that if you have a large sample size and you scale things, like you scale your random variable by the sample size, things look symmetric. So it says for large samples, things look approximately normal. That's why when your sample was pretty large, it actually changed. Look at what happens to distribution. See, for large samples, it looks really symmetric, right? Instead of looking T, it actually looks symmetric. But the same thing is actually true for the skewed thing here. So suppose I change my sample to, let's say, I don't know, 1,000. Let's see what happens, just out of curiosity. It's always a good exercise to check these things. Let's run it and see what happens. Not this one. This one here. Not this one. Why? Because I can make this one symmetric, but I need to recenter it. But yeah, what happened with the T distribution is that for large samples, things look more symmetric, right? And I can actually show you the T distribution to see why this is true with T distribution. You can see that actually, yeah, the T distribution table. You will see that for large samples at some point, the T distribution just looks normal. So I should be able to show you my own thing. That's actually why if your data is T, guys, you can still use the T distribution. So if your data is at all symmetric, you can still use the T distribution, but if it's not, please don't use that, right? So you will see here that for large samples, this is actually the quantiles, the normal distribution. That's why when your data is very, very large, the T looks like Z. which means that if your data is actually symmetric, you can still use the t-distribution. You can use the t-test. But if your data is skewed, please don't use it. So if you truly have something that looks like this, where it's seriously right skewed, you probably shouldn't use the t-test. But like I said, if your data is even a little bit, symmetric, like it's T instead of Z, feel free, you can still use the t-test, right? So the t-test is robust to slight long tails, but it is not robust to extreme skew. So you can still use the t-test for things that are symmetric with t-distribution, but you should not use it for things that are highly right skewed, right? Okay. I just gave you an exercise here. You can try it yourself as well. Like try to see what happens. The t-distribution looks more symmetric, but the gamma being truly actually right skewed, it just becomes more right skewed. You cannot actually use the t-test for that. Now let's look at the data, right? Let's look at Professor Butler's example. I don't know, did you guys learn match test yet? Can you guys let me know in the chat if you've done like dependent t-test? So if not, I can skip it because I want to show you guys the line test. So have you guys done the matched t-test? Let me know in the chat. Oh, it wasn't the lecture. Okay. So I'll just go over it quickly because I do want to spend 10 minutes on the sign test and how to know to use it. Anyways, this is his example on pain. So if I look at the pain data here, you'll see that, oops, I called it pain origin, sorry. You can see that you have a subject number and you have two different drugs. So each subject was given drug A and drug B. The question is which one's better? Sometimes you use matched pairs when you're doing repeated measures in the same subjects, or when the subjects are related in some sense. It's matched when in this example, obviously, because you're measuring the same subject twice. That's to control variability, obviously, because when you measure the same person twice, because their variability is consistent, the difference would be the treatment effect. But sometimes you also have a matched pair on the mother and daughter, like father and son, where there's a clear relationship. So the matching doesn't have to happen on the same sample. It could also happen on like two samples that are related in some way or have a correlation. But anyways, if we're performing a t-test that was independent, we would do this in the following way. We'll give the data frame. So width is a function that allows you to feed a data frame and do the test. So width, the pain origin of the data frame, t.test is the t-test I'm performing, and I'm looking at the difference between these two different groups. You can see that if you perform a t-test with independent groups when you know it's not, we get a p-value that's not significant, right? The reason why it's not significant is because your t-test for independent samples is assuming the following. You're taking a difference on two independent groups, right? It's assuming you're doing this, right? If it's pooled, let's assume that it's pooled, right? But because you have different subjects being sampled twice, this variance is actually a lot larger than it should be. So the standard error is a lot larger than it will be under independence. And so it shrinks the actual effect because this will actually end up being bigger when you assume they're dependent. It will actually shrink the effect. So we probably should not use this independent t-test because it has implications on the standard error down here, right? And I'm not gonna get into too much of the stats because it's not important, but it'll have implications on the standard error, which will actually end up resulting in an incorrect conclusion. But anyways, you can see that it's actually looking at whether or not the difference in means is zero. That makes sense. You want to assess if the two different means, you want to know if the drugs are actually consistent, like they're both equally good, and you're looking to see if the difference is bigger than zero or less than zero. So you can know which drug is better than the other. It's saying that zero is in the interval, meaning that zero is a plausible mean difference. You cannot negate the null. If zero is in your interval, it means that you don't have evidence to reject the idea that potentially you have no difference in the drug therapies. That's the independent test. But this is not actually matched. So we did an incorrect test initially. Why? Because the within subject differences will actually result in a standard error in the denominator that's larger than what you assume for an independent t-test. This will give you a larger p-value, right? Why is that? Because it will tell you that your t-test is not significant. This will shrink the t. This means that your t will go down to zero, basically, right? So your t will shrink to zero, and actually I should call this t. Your t will shrink to zero because this is going to increase this thing here. This thing here, I'll put it in red. this increases, and it will drop your t-test down to 0, right? So when you look at the actual t-distribution, it will make it closer to this region here. It'll be closer in this region here where you have a high p-value and you cannot reject the null hypothesis, right? So it will actually shrink your t-test because the large within standard error that from the results and the fact that you have different subjects are not actually accounted for. So we can't use that basically. However, now let's change this. The way to change is to put parity equals true, to recognize that it's the same subject we measured twice. Let's see what happens. Notice that your test is still not significant. Your p-value is still bigger than alpha, but narrowly, right? So you can see that it narrowly results in a failed to reject the null hypothesis. Again, this is because now you are accounting for the fact that you have a big within group difference because you're measuring different people twice, and each person is a different measurement on their variability, basically, right? So your p-value actually decreases because you're now accounting for the standard error that is different between the different people, right? But let's be a bit more careful here because perhaps the fact that our data our significance is narrowly failed to reject the null hypothesis means that our data is not actually symmetric. So you can see that once you've accounted for the fact that you don't have an independent group, that you're measuring the same people twice, and you take care of the standard error, which then obviously shrinks your p-value because your p-value is now going further into the tails, into this region here. It's still not significant, but we should make sure our data actually is symmetric. If it's not, we need to do another test, basically. So I'm going to check this. First, I'm going to actually mutate. I'm going to create another data frame. I'm going to create another column of my data frame that actually is called pain diff. It takes a difference of my two variables because I need that for my t-test, right? As you can see here that you need this for the t-test over here. So I'm going to do that. So I've called it pain. I've called a new variable called, I've called a new data frame pain. So if I look at it, you can see that it added pain diff, which is a new column in my data frame. But it has all the other old data frames. It has all the other columns. I just added a new one called pain diff. Sometimes when the difference between drug A and B is negative, you'll see negative. Sometimes it might be the fact that it's positive. That happens in, for instance, observation 4 and 6. So you can see that we're going to add up all those mean differences. And that will be our grand mean difference, right? So you can see that we've created another column, adding mutate. And now I'm going to plot this. I'm going to plot my pain diff to see if, because I'm going to plot pain diff because I want to see if it's actually normal. If the difference is not actually normal, I got a problem with my task. You can see that this here, this difference here, we're assuming that x1 bar minus x2 bar is normal with a mean of 0 and a particular variance given to us as the following. That's what we're assuming, right? But if that's not true, we need to know it. So that's why I'm looking at the box plot to see if it's actually symmetric so I can make changes if it's not true, basically. So if I plot this, I guess it looks like this. And I guess I could flip it so you guys can see it a bit better. So let me just do that. Word. No, flip. Okay, so let's flip this so you guys can see it a bit better. So you get this. There is a big lower outlier, ironically, because the distribution looks sort of right skewed. I noticed that the median is closer to Q1 than it is to Q3, and it has a slightly long right tail over here than it does to the left. However, there's a lower outlier. So it's very strange because while it looks sort of right skewed, there is a lower outlier. So I just want to point this out, that the distribution has a lot of weird things going on, right? So it has a lower outlier, but the actual shape of the IQR range, like between Q1 and Q3, looks sort of right skewed and has a long right tail. So there are many things to take note of here. But anyways, let's look at the actual QQ plot to substantiate our idea that maybe it's not actually symmetric and we cannot use the t-test. So you can see it looks like this. The problem is that we have this big outlier over here, right? This is probably a bit of a problem, basically. Okay, so the question is, should we use this t-test that relies on sort of this notion of a symmetrical distribution when we have this big lower outlier? I'm not sure. And like what do we do when we don't have this notion of what should we use when our data is a little bit funky? Should we use something else that relies on the median instead of the mean, basically, right? So this is where we need dev tools. So if you haven't run it during the tutorial, that's cool. You can watch me, but please, if you came in late, go back to the beginning of the tutorial when I post the video. It will show you where in the lectures you have to find the installation ideas, because you might need this for your exam, right? So where you have to know some certain things, if it's a take-home exam and you have to run certain ideas, and then re-upload it back onto Quarkus. If you cannot use SMMR, it might be a problem, and he's probably expecting you to check, but there is no assignment due this week. So if you don't actually check it yourself, right, there's a problem. So please check to make sure it loads before Friday, which is your midterm. Okay, so now I need the DevTools library in order to run SMMR, because I can't, you need install.github is inside the actual DevTools package. And his SMMR is not in Crayon. It's on his GitHub. So you can't actually use it until you actually install SMR. Okay, so so sign task. What do you have to do? You have to give it a data frame, which I called so sign task. I guess I don't know if he actually has the sign task help in Crayon, because if you use help, assuming the package is in Crayon. So I'll just tell you what it does. And it's not in Crayon, you will not find it in the help function. You need to give a data frame, then the variable you want to compare the difference on, and then you're saying that you think your median is 0, right? So you're doing your data frame is pain. The thing you're looking at is pain diff, and you're looking to see if it's actually different from 0, right? Now I think this is actually a binomial thing, right? This is actually a binomial thing. Right? That's okay. This is actually a binomial thing, basically, right? So you can see you're trying to see is the median different from 0, basically. So I'm going to run this and show you what you get. So 9 are below 0, 3 are above. So I'm trying to see how many of the observations are below 0. So pain diff, remember, is actually my data frame. So if I look at the length, sorry, it's not my variable base. If I look at the dimension of pain diff, you'll see that it's got a length of 12 because there are 12 observations, right? So it has a length of 12 because there are 12 observations. So I'm trying to see how many of them are above and below 0. 9 are below 0, 3 are above. The question is this significant, basically, right? So you can see that if your median is truly 0, guys, you should expect to see about 5 and 5, 5 are above and 5 are below. So I would give you a p-value that's not significant, right? So what you kind of expect to see, right, is sort of a p-value that says like, well, half are below, half are above, and so that it's not significant, right? But the extent to which your actual p-value is showing a difference that is not equal on each side, it gives you a hint that maybe you don't have a symmetric distribution. But we also saw that a bit from our QQ plot here. Like when we looked at our QQ plot, it showed us a right skew thing, right? So that, because it's right skew, that's how we have a lot of observations below 0, right? Because remember, your median is closer to Q1, which is low. So you would have a lot of observations below 0 because your median is closer to Q1, that it should be lower, basically, right? So now the p-value here is the following. If we're doing a two-sided test, the p-value is actually 0.072 times 2. That's what we actually, okay, we're taking the lower. So we're looking for p-value, we're looking for lower, basically, right? So we're looking for p less than, so we're looking at lower, but you can see that this is a two-sided test. So we have to multiply our p-value by 2 because it's a two-sided test, and you'll see that it's still not significant. Ironically, that kind of tells us that our initial t-test, or we didn't have significance, is probably kind of correct, right? Even though we shouldn't have used the t-test for the way the data looks, even when we use a sign test, it still doesn't show a significant result, right? So with a data set that is so small of only 12 observations, a difference of 9 and 3, you can't really tell much about it, right? So if you double it and you have the 18 and 6, maybe you see a significant result, but with such a small data set, you actually can't make conclusions so much about the p-value. You can't make conclusions, sorry, you cannot make conclusions about the significance being like radical with a difference of 9 and 3, right? So we don't have evidence to reject the null hypothesis because we're taking the lower one here. We want the lower, right? We don't have evidence to reject the null hypothesis here, right? The sign test is essentially looking at how many values are above and below a specified median, I should say, not mean. Sorry, mean. The moods test is kind of similar to the median. The moods test is similar to the sign test, except the difference, instead of looking at the different, is the mood test similar to the sign test, except the sign test looks at the mean, whereas the mood test looks at the median, basically, right? So here it looks as if when we're looking at a difference of 0, it's still not significant using our sign test. By the way, the sign test is based on the binomial distribution. I don't know if you guys know this, but the sign test is based on the binomial distribution. It's looking at, it's actually looking at a binomial distribution, right? So even though it's still centered at the mean, right? So even though you're looking at pain diff and whether the mean is different from 0, it is still actually centered on the mean. It's using a binomial test to do it. So you could actually think to yourself, if your data is heavily skewed, you shouldn't use the mean at all. So you should use the median. So just to be clear here that the sign test still actually looks at the mean. So it's still assuming some notion of symmetry. If your data is heavily skewed, probably you should use the mood test instead, where it actually orders the data based on highest, lowest, and it's looking at the actual median instead of the mean, right? So the sign test is still looking at the mean as your measure of the center, whereas the moods test looking at the median, right? So if you deduce your data as heavily skewed, you probably should not use the mean, right? You probably should think about using the median or some other mood test, right? So I don't think I'll have time to talk about the moods test for this tutorial, but I will talk about it for the one that's starting at 10 to 11. So that means for those who didn't see me talk about the moods test, which is now using the median instead of the mean, you can watch the video later because I think that the moods and the median test might be on your midterm. So I'll talk about it a bit in the 10 to 11 class. But yeah, just to be clear, the sign test is still looking at the difference in the mean, whereas the moods test and the median test are ordering the data and looking at the median, right? So we have still looked at the mean here. The difference here is that instead of using the t-test, we're using the binomial. So we're looking at the binomial tells us, well, if you have a certain amount below the mean or a certain amount above, what's the p-value for that? So just to be clear here, we're using the binomial distribution, but we are still centering the test along the mean for the sign test. Whereas with the moods and the median test, we're centering along the median if we have very skewed data. And that might have an impact on the actual, you can imagine that would have an impact on the distribution, on the p-value potentially, right? If you center the test in the median instead of the mean. So just to be clear, so far I have not centered any tests on the median, but I will in the 10 to 11 class. And I apologize that we ran out of time, but I will post the video. So that means that for those who did not see the median and moods test, certainly you'll see that when I upload the video. But for those of you who are here for 10, I'm going to pause for a bit for 10 minutes, then we'll come back and continue the lecture. Oh, tutorial. I'm going to pause now. Right. I was telling you the class your midterm is this week. It's Friday. I don't know what time. I definitely know it's the 18th. Today, Ken is going to teach you guys the median test, which is on your exam. So definitely make sure to watch your lecture. Make sure to attend the lecture if you can. But if you haven't watched it, please, as soon as you upload, definitely watch, because the last thing you want is to wait till the last minute to make sure packages are loading on your computer, or to understand how to manipulate the functions and then realize something went wrong where you don't have time to ask Ken because it's the night before or something. So definitely watch ahead of time or attend the lecture. Don't be the person who waits till the last minute to get their work done. I'm going to use empty cards. It seems this is my theme in this course. It's just kind of built into the data frame. Don't use this function I'm going to show you here. This is built in base R. You should not use it. There's a function in tidyverse he probably wants to use for qqplots. This is just using base R merely because I want to show you the similarities in tidyverse, but to be clear, you cannot submit this kind of function to your midterm or any assignment because this is base R. I'm going to use the weight variable. That's why you can see I attach empty cars. So my first instinct is obviously to attach empty cars, right? Because when I attach the cars data frame, then I can use the variables externally, right? Within the global environment. So you can see I'm using weight. I want to know if weight is normal, right? So let's run this. On the first line, you cannot tell because you don't have a theoretical line to make a comparison on. You need to use QQ line if you want to actually see the line come up for your plot. And I'm going to tell you what it's actually doing. Because I noticed with a lot of these SAS courses, people just, people look at the QQ plot and they say, oh, it's normal because it's following the line, or it's not normal because it's not following the line, but they don't really know what that means, right? So I'm going to just take a couple of minutes to explain what it actually is. I made this graph in the previous tutorial. You can see on the x-axis is the actual theoretical quantiles of the standard normal guys, right? So remember the standard normal kind of looks like this, right? It's centered at 0, has mass kind of around 3 and -3. While it's defined over all of R, it doesn't really have much mass beyond -3 and 3. Our data has a distribution. If our distribution for the data is normal, with the mean and the variance of sigma squared, then when you look at the actual, you should be able to transform your y to z. So you use the transformation you guys saw, it looks like the following. Right, so the transformation should just transform your y that is normal to z. So there's actually, and this is, you can see this is a linear map base. This is a linear map. Right? Because this is a linear map, there is a one-to-one correspondence, guys, between y and z, so that when you look at the quantile, you should be able to map out, if this is x, then for given x is a y, this, your data places, your data has a one-to-one map correspondence with, right? So for given x, there's a y, because it's linear, there's a one-to-one map, there's a one-to-one correspondence, right? Your data is actually normal because you can transform your y to z. You should see the points trend the line pretty well. If your points don't trend the line very well, you get things that look skewed, and you can tell from the QQ plot, right? So one thing I said was like, if something is right skewed, you can see that when your sample size is very large, the points trend off the line like this, where because, and the reason for that is because your distribution is right skewed like this, but the normal distribution kind of does this. And so you can see that these points over here, the normal distribution doesn't have any kind of one-to-one correspondence with. So those points fall off the line to the right like this. And the same thing happens for left skewed things, right? Because again, the normal distribution doesn't really see the points that are way back there, right? When you draw it, it kind of does like, it doesn't see these points over here. Maybe I'll just draw this a bit better. So when you draw the left skewed thing, you can see that it also doesn't see, when you draw the normal distribution like this, it doesn't see the points over here similarly. And so you can see that's why it falls off the line in the following way when it's left skewed, just falls like this, right? So when you have skew in either direction like that, you probably should not use t distribution. And so that's why logically Ken has the lecture for t, sorry, it has a lecture for the sign test paired with the QQ plot, because you should be checking for these kind of things before you actually do a statistical task. Because if you were to ask you a question in the midterm, it says something like, you know, perform a statistical test, he may not tell you what test perform. He expects you to look at the data and determine if your data is actually symmetric or centered. And if it's not, you probably should not use the t-test, right? From this data, this is the weight variable. Based on this, it's, first of all, let me show you how to do it in tidyverse, and I'll kind of explain what's going on here. you can actually see that, right. I made a random variable that is normal. Oops, I made a random variable basically, right? That is a kind of, what do you call it? It's normal, right? Oh my gosh. Right, so you can see that our norm, if I just show you what it's doing, if you don't give it a mean and variance, it's going to assume that it's 0 and 1. Okay, so I wanted the mean to be 3 and the variance to be 1, and the standard deviation to be 1. So actually, just to be clear, that puts it takes standard deviation, not variance. Be careful about this, right? If you're given variance by canon your actual assignment, and you want to do something with our norm function, make sure you square root it first. Anyways, so the reason why I first actually plotted, I actually first plotted it using, so I'm going to show you the histogram. I'm going to show you the histogram. Oh, someone asked a question. Oh, so the reason why I put set.seed, Layla, is because I'm being a bit lazy. I actually don't want my points to move. If I don't, oh, that would just because my birthday is October 21st. That's me being a bit vain. Sorry, you can choose whatever seed you want. I always choose, it can be any number. It's just that when you put a different number for the seed, it would change the values you got, right? So if let's suppose I put the seed of 1, right? And then let's suppose I set the seed to be 2. And then I look at, let's say I call it, let's call it M. N is equal to our norm, 32, 3, 1. You will see that because you started at a different point in the list, the numbers you pull is different from Z. Or you can see it's not the same because you pull different numbers. You started from a different part of the permutation because this is a collection of numbers that are generated from random normal, right? If you set the seed differently, you take a different starting point, then the numbers it randomly pulls will be different. That's still, it doesn't really matter, but the numbers it pulls will be different basically. Yeah. So I just put 1021 because it's my birthday. I know that's probably a vanity, but so yeah, so you can see that I'm just gonna first show you how to make I'm gonna show the histogram, and you shouldn't do this, but this is me because I'm using base R first because I did not create a data frame yet. And you can see that if you try to put Z into, if you try to do the following over here without first creating a data frame, it will not run because you see that qqplot takes a data frame first before you map to a coordinate system, right? So this is data frame mapping to a coordinate system. You cannot put in Z because that is nothing more than a vector. It's not actually a data frame, right? So this is why I want to just look at the histogram quickly. So I have to first use base R just because I have not actually created a data frame, right? So if I do this, I will get the following. I guess maybe it looks like this, which makes sense. It's a normal thing, right? So I know it's centered around like 3 and it's normal, right? I'm gonna create a table now because I want to do it in base R. Like I said, please don't use base R. I want to use tidyverse. Please don't use base R in your work, right? So this whole course in tidyverse. So even though it's easier to put hist of Z, it's not what we do in this course, right? So I want to show you guys what the ggplot looks like, and it probably should. Let me just do this. You'll see you get the following. It looks like this, which is awful, right? So I need to change the bins basically. See what happens if we put 10. Probably I should put 5 or 6, but let's see. Let's change it. Let's lower it. So you have sparse data because you only have 32 observations, so you can't have too many bins. Let's change it to 5. Looks a bit better, but a little blocky. So let's change it to 6. So now you see that you cannot always, when you have sparse data, your bins look kind of messed up sometimes. You have to be a bit careful about your data. Yeah, there you go. Let's leave it at this. it's based on your data size. So you see that the default is to use, I think, 32 bins. But if you don't have a sample size of, let's say, at least 100, 32 bins looks bad because you will have sparse data. I would say if your data is like below, let's say 30 or around 30, you might think to use 5 to 6 bins. If it's around, let's say 50 to 100, you might use 10. If it's bigger than that, you could use the default 32 bins, but it depends on your sample size. If your data is small, you would imagine you have sparsity. So if you don't change your bins, the problem you'll get is that it will show you blank spots because you cut your partitions too fine, basically. If there's 1,000 data points, you can just use the default. The default is, I think, 32 bins. Yeah. If you have a large data set, then you can imagine you probably have observations in every bin. If your data set is small, you would have some bins that are empty. So it will look bad, and it'll be difficult to determine the shape of your distribution that way, right? So it's entirely dependent on your sample size. Okay, now let's look at the QQ plot, because I want to show you guys what happens when you actually think that something is normal. So notice that the reason why I used base R before is because you can see that if I want to look at the QQ plot, similarly to how I use it in base R, yeah, you have to, it depends on your sample size. If you have a large sample size, you can play around with it, but if your sample size is very small, you shouldn't use, your bin should probably be around 5 to 6. Okay. So you can see that similar to how in base R, I had QQ norm, then I had to put the line. You need to do the same thing here. If you don't put stat line, it won't give you the line, then it will become difficult to determine if your points are turning the line properly. So let's run it. You see it does this. This is pretty symmetric. It makes sense because I sampled something that's normal. I already know that it's normal. That's why for the most part, the points turn the line. But what happens if you didn't truly actually have data that's kind of normal? Actually, somebody asked me in the previous tutorial, why did you use Tibble? What's the difference between data frame and Tibble? I said that for the most part, Tibble and data frame are the same. But the only difference between data frame and Tibble is if you want to use table function in base R. If you want to do, you know how you guys have 2x2 tables and stuff? You've seen them before. Where you're looking at like how many categories you have in each section in a 2x2 table. If you want to make a 2x2 table, you have to use Tibble, right? Because you can actually do things like table of data. So if I do table of Z, this is bad, obviously, because there's only there's 32 different observations, but they're all different. However, you can see I can actually do table of Z. You can actually do table of Tibble. You cannot do table of data frame, right? So if you really wanted to create a table that shows you the frequencies of your categorical data, you can use Tibble because you can put the table function in table. I don't believe you can put a data frame into Tibble. That's why sometimes if you want to make tables to show your categorical the frequency of your variables, you cannot use data frame. You have to use Tibble. So that's really the main difference and nuance. But for the most part, they have the same operations, except when you have that problem there, right? When you want to use table function. I don't imagine for this course, you'd really be using table functions, so probably you will just be using, you can use table and data frame interchangeably in this course. Anyways, let's see what happens if we sample something that actually truly is, right skewed. So everybody knows that R gamma, because you guys all took B57, I think, so you have to take it, take this course. R gamma looks something like, it's like very right skewed, right? So if you put it looks to me like this, where, it's pretty right skewed. It has like very low frequency, it looks like this, right? So this is gamma. It's pretty heavily right skewed, and I'm going to show you what that looks like. So I'm going to set the seed again to my birthday. So sorry. Now, if you look at the gamma function, you can see that you have to give it a sample size and a rate and shape. So my rate and shape is just 1, 1. You guys know there's a different reparameterization for the gamma function. You can divide it by scale or rate, where scale is the inverse of rate. You have to make sure you specify that, right? So if you want to use scale instead of rate, you should state it, right? You should say scale equals, but otherwise, I believe the default is just to take the rate. I just took shape and rate to be the same. But like I said, if you want, there's a reparameterization of the gamma function to be the inverse of rate. So make sure you're aware of this, right? So I'm going to just show you guys what the histogram looks like. So I did make a note here that I used base R instead of histogram. I used base R hist instead of ggplot because I have no data frame basically to give. So I'm just going to do this. Yeah. So if I do the histogram of this, you're going to see that it's very right skewed. So it looks sort of like this. This is very right skewed, right? Which is great because now we get to see the features of what happens. So remember, I recall I said the following is true. Your data looks like the red when it's right skewed. We'll see if that's true. We know this is certainly right skewed. It has a long right tail and the median is closer to Q1. It's very far back. Okay, so let's make it tibble because I cannot feed a vector into ggplot. So if I do this, oh, I don't need this. If I make the ggplot, what do I get? I get this. Right, what do you guys notice about this plot? There's like an upper cup, right? There's an upper cup. It's like it's almost like it's pointing upwards because your data points. Remember, the normal distribution is assuming something like this, and your points are like far. You have these points far above it, and even far below it a bit. That doesn't register. That's why you have these points over here that are off the line, as well as the points over here that are off the line. Because the points in the over here and back here doesn't register. It's not doesn't register them as something that you should see on the quantiles. The normal distribution. Right, this is why you see this upward cap. And if you pick something that is left skewed, like you take a beta distribution and you make it left skewed necessarily, it will show you the opposite. You'll see a downward cap because it also doesn't recognize the very extreme high and low values because it's not centered, right? So I can even change this to 1,000 and it will be even more right skewed. You will know you really cannot use the t. The reason for this, the reason to show you this is that you can see it does this. You seriously cannot use the t-test for this distribution. It will yield false conclusions. When you use the t-test, so what is the t-test assuming? T is equal to y bar minus mu over s by root n. You remember that y bar is approximately normal. It's a mean 0 and a variance of 1. S is, it's the square root of a chi with degrees of freedom k. You have a ratio of a normal and a chi. Now, if your y bar is not normal, this whole thing is off, right? So now we know that when our data y is actually right skewed, this t-test is false because it's not even a ratio. It's a ratio of a right skewed thing over a chi. It's not actually normal, right? So we can't actually use that test because it will give us false conclusions, right? So that's why we have to check about the characteristics of our data to know if the test we're using is appropriate. Now, the t-test is a bit of a funny one. I actually did also draw that here. You can see that it's the blue one here. It has kind of a funny thing where in the middle, it trends the line pretty well because it's symmetric. You guys know the t-distribution is actually symmetric, kind of like the normal distribution, except it's a little twist. Well, the normal distribution looks like kind of something like this. The t looks something like, I don't know, something like what? I think it's red, something like this. Right, you can see that oh, that's not very good. I want to center in the same place. Well, it centers at 0 the same way the normal distribution does. It has it flattens space because the tails are long, it's flat. Whereas the normal distribution has shorter tails and on a higher mode because it puts most of the mass between 0 to 1. The t distribution kind of flattens because it puts the mass even towards the tails, whereas the normal distribution does not. You guys know the normal distribution kind of likes to stop at 3 and -3. Where most of the mass is concentrated around like 0 to 1, basically. Let's say even like 0 to 2. Really, actually, you can know that 84% of the data is between -1 to 1. That's like, that encompasses like, sorry, this encompasses 68% already, right? Between -2 to 2 is 95. You guys know that 99 is between -3 to 3, whereas the t-distribution will actually encompass less between -1 to 1 because it's flat, basically. So anyways, let's see what happens if we set the seed and we run our thing. I'm gonna run it a bit, line by line. I wonder if I can, so let's see what happens if we run this. So RT, by the way, guys, is It's the random variable for t-distribution. Notice that you have to specify a sample size and degrees of freedom, but the degrees of freedom is n-1. So once you fix the sample size, you've implicitly fixed the degrees of freedom. Because I fixed the sample size of 32, my degrees of freedom is 31, right? So once you fix one, you fix the other basically, because they're functions of each other. Okay, so I'm going to run this. Now let's look at the histogram. It looks like this. You can see that it's still centered at 0, but it's flat, right? You can see that it's sort of flat, whereas this would not be true for standard normal. If you look at the normal distribution, right, it would look a lot more tight instead of flat, right? And actually we can go back up and look and see, I think, because we did this up here. Look at the histogram. Let's put this 0 instead of 3. If you put it at 0 instead of 3, you'll see that it will look, oops, let's run this here. It will look tighter, right? So, no, oh, this is not very good. That's because the sample size is small. Let's increase to, let's say, 50. You can see that it looks tighter around 0. So while it's certainly true that they both peak around 0, not in the same way, right? So that's something we have to be a bit mindful of, right? So anyways, let's make a table of this and look at the QQ plot. Now that we know that it looks kind of funky, it's certainly symmetric, but it's flat. Let's see what the implications would be for that, for the QQ plot. You can see that it's certainly doing a good job in here, guys, right? But you can see that it's starting to fall off the line this way, right? You can see that it's starting to fall off the line over here because the tails are long. And it doesn't, the normal distribution won't register things that go out like this. It doesn't register things that the points that are too much past -2 and 2, because that encompasses 95% of the data. So for the normal distribution, you can imagine that between -2 to 2 is actually 95%. That's a lot of that's actually most of the data. So it doesn't actually register stuff that's too far out. That's why these are falling off the line, basically. Ironically, guys, if I increase this to, let's say, 1,000, let's see what happens. It's kind of a funny thing. You will see that it looks like this. Anyone know what happened here? I think this is kind of neat. This is like our theories making a lot of sense. Does anyone know what happened here? And I'm going to actually pull up my T thing, my T table. There's something called the center limit theorem, which says that for large samples, your data looks somewhat symmetric or somewhat normal. Not even just looks normal, regardless of the underlying distribution, right? That when you center things by its mean, when you literally center things by its mean, and you scale by a factor of root n, so it says if you center things by its mean, and you divide it by its s, when you center, right, things look somewhat symmetric, right? For large n, asymptotically, n being the sample. Because T is equal to y bar minus s over, y bar minus mu over s divided by root n, implicitly the T distribution is already a centering of your random variable by its mean, times the scaling, right? You already have it in the form of the random variable minus its mean times the scaling factor, which means that it actually approximates the normal distribution more and more when you make the sample size large. That's why these are actually the quantiles, guys, of the standard normal. So for large enough n, the quantiles of the T distribution actually looks like the normal distribution for very large sample sizes, right? That's why you see your QQ plot looks normal when you drive your sample size up that large, basically. But if it's smaller, that isn't true, right? So because the sample size was so large, you saw that it drove the actual distribution to something that looks like normal. And you can see it in the table too, where it will look more and more. You can see it here in the histogram. It looks really normal. The mode is high and it doesn't go beyond like -2 to 2, right? So this is the table actually says when your sample size is large enough, T will become Z because the scaling, because you centered around your mean and you scaled it by root N. That's true not just for the normal distribution. That's true not just for T, but for all distributions. The reason why this one didn't become more symmetric when you increase the sample size is because you did not actually scale it by its mean, right? It's just, all we did was actually increase our sample size of a very right-skewed distribution. We did not actually scale it by its mean and divide it by a standard deviation. It's still actually something that's really right-skewed. We haven't scaled it. That's why it looks like that, even for large sample sizes. That's central limit theorem, Jeffrey, exactly. The reason why this one does not look normal is because we have not actually scaled it by its mean. It's just we just make, when you increase the sample size, all you do is make it more and more right. So you do not scale it by its mean, right? Because T is implicitly y bar minus mu. It's the scaling. There is no scaling performed on this right skew thing. So it just looks more right skewed in the limit when you increase your sample size, right? So, but it's a good thing to know because for the T distribution, for data actually is distributed T, you probably can use the T-test. Even if you have like big outliers, because the T-test is robust in some level to large outliers, especially if your sample size is large, because it looks more and more normal. But it's not true for things that are heavily right-skewed. We cannot use the T-test for highly right-skewed distributions. It will yield something that's very incorrect in our analysis. So if he doesn't tell you if he just says perform a statistical task, is your result significant? You have to logic out to yourself if it makes sense to use the T-test. So you have to look at the features of your data and make the decision for yourself, right? So if it's, and you should even use, you should even make the decision as to whether or not you should even use the mean at all as a measure of the center. And you have very highly skewed things, the mean might not even be a good measure of the center. You might want to use the median instead, which is why he actually introduces the median test this week. It's because if you have highly skewed data, like you saw with the gamma, the mean is really not the thing you want to use to compare two groups, right? So anyways, let's look at an example from the prof's lectures. So I'm going to use the pain. So this is a pain test. So you can see that they're looking at two different, so let's see, pain origin. They're looking at a test. They're trying to see which drug is better. And so naturally, to control the variation you have between subjects, one thing they thought to do was to perform a study where they've actually given the drug to the same people twice. This is actually in some sense easier than matching people based on similar characteristics, which you still cannot control the variability that way. Sometimes independent groups don't work in drug therapies because it's easier to control the variance when you measure the same person twice than just to match people in a characteristic, which is hard, right? So that's why sometimes in drug therapies, they tend to use repeated measures because they can keep the variance between people low when you're looking at because any effect you see in the mean difference between person one with drug A and B is attributed to the drug because you measure the same person twice, right? So whereas if you had a match thing where you match people based on characteristics, you wouldn't know if the effect you saw is the drug itself or the difference between the two different people. So trying to control the variation you have between people by measuring the same person twice, that way you know the difference you see in the drug therapy is entirely due to the drug itself. Not entirely, because you can certainly know there's features different between people, but it's primarily due to the drug instead of the variance you see between two different people. So this is what you have here. If we do an independent t-test, we know that's wrong, right? Because we can see that we're assuming that the people in drug A and drug B are different, when in fact you measure the same people twice. So you cannot, we know it's wrong, but we do it anyways. So the width function tells you, the width function is kind of like provide a data frame and the expression you want. So width is a function that allows you to perform a test given a data frame, right? So it's like, give the data frame you want me to look at and what expression do you want me to perform? Here it's a t-test. So I'm going to run this. You can see that you get this. It's assuming that you have different variances between the two different groups. But you can see the p-value here is not significant because p is equal to 0.3077, which is certainly bigger than 0.05. In this way, we would say that there is no difference between the two different groups in terms of between the two different drugs in terms of pain. Another way you can tell, guys, if your test is not significant without seeing the p-value is look at the confidence interval. Notice that 0 is covered in that interval of -6.34 to 2.1277. Whenever 0 is covered in your interval, it suggests that you don't have plausible evidence to negate the fact that mean could possibly be 0 is possibly true, right? So if your null hypothesis is the following, mu1 minus mu2 is 0 versus the alternative, no, they're not 0, right? If 0 is covered in the interval, you don't have evidence to negate this. What it's saying is that it's possible the actual mean difference between drug A and B is truly actually 0, right? So you don't have evidence to negate that, so you don't have a significant fact. I can see that from the confidence interval without even looking at the p-value. The problem with this test, though, is that we know that we don't have independent groups. Even if we assumed pooled, so this, I'm going to assume it's pooled. Suppose it's pooled, and let's change it. Right? If I just even do pooled, all right, that's fair. Equal, let's suppose we have equal variance when we're doing a pooled test, right? So let's let us assume we have equal variance. So I'm just going to stick that in. The p-value is still very high, 0.3. So you can see that the problem is that if you have pooled, the test t is equal to y1 bar minus y2 bar minus mu1 minus, so we have this. This is pooled, right? The problem is that the denominator, the standard error is going to be actually a lot larger than it should be, because you have not accounted for the within group variability. You have not accounted for the fact that within the individuals themselves, they have a high degree of variability, right? Because you've assumed they're independent groups. You have not accounted for the high degree of variability within each person in the sample when you do this. And so this actually makes the denominator a bit bigger than it should be because you have not accounted for the within group variability, right? You've assumed that it's 0, right? So when you have a covariance, it doesn't, you guys know you're looking at the variance of like x1 plus x2 in random variable. This is the variance of x1 plus the variance of x2 plus the covariance of x1 and x2 plus 2 times that, sorry. When you assume independent samples, you assume this covariance is over here is 0, but that's not true, right? So you can see that you've actually made a big assumption that is false, which is going to push up the standard error in a way it shouldn't have been pushed up if you had accounted for the difference, basically. Actually, should be minus, by the way. It should be this. Anyways, it doesn't matter. Yeah, so you see you have a problem, basically. I said this should have been minus because I'm looking at the difference between two things, but it doesn't matter. The actual variance will be the same, ironically. Anyways, you can see that you would have not accounted for something you should have accounted for. And that's a problem, right? And this should actually be minus, I think. This is minus. So you see that you should have subtracted, because you assume this is 0, instead of subtracting the covariance structure, you did not. You actually pushed up the standard error in a way you should not have, which resulted in your t-test shrinking. Because what happens is that when this standard error in the denominator is bigger, it actually pulls the standard error down. So we'll actually shrink your t-test. We'll shrink it down to 0, right? And what that's actually saying is that it's saying that your t statistic is closer to the region here where you failed to reject the null hypothesis, which is why your p-value is so big, right? It's no longer in the tails because it was shrunken by the large standard error in the denominator, right? You can imagine if I actually just stick compared equals true. So So if I just, if I just stick in paired equals true and I just use the same variance equals true, actually, this is no longer important. We'll just assume it's a paired t-test. Let's see what happens. You see your p-value actually goes down. Because you've now accounted for this covariance structure you did not account for before, it actually pushes your t-test closer to the tails. Actually, it's actually bordering, it's borderline, it's bordering significant. That's now, instead of being so far, it's like kind of here now. Let me put it in a different color. It's like bordering, it's like here somewhere. So something that's still failed to reject HO, but it's closer now to the border where you might possibly reject it if you might possibly reject the null hypothesis. You still won't, because it's still bigger than alpha, but it's only narrowly now bigger than alpha. Right, so it's getting closer to the tails merely because you adjusted your standard error. So you can see that if you don't have the awareness of what I'm at, if you're doing a pair test or an independent t-test, it can have implications. But we can go further than this, because we didn't really actually check, guys, if the t-test is appropriate at all for our data, right? So even though I addressed the fact that it's a paired test, I should still check to see if I should have used the t-test at all. So I have to check about the structure of my distribution, because if this distribution is not actually symmetric, I probably shouldn't have used the t-test at all. So let me just check this basically. All right, so first of all, I'm going to make what I want to do is I want to check the distribution using a box plot of my, of the difference variable. So I'm going to take a difference of the actual, the drug A minus drug B, but I'm going to add this vector into my data frame. So I'm going to call it pain diff, and I'm going to call the new data frame pain. So if I look at pain, and I can see that it has this extra pain diff. Obviously, if the difference between drug A and drug B is negative, so that means that drug B is, the effect is bigger than drug A, it will be negative. But in certain situations where, like for instance, like observation 4, you might have the opposite is true, where it's positive. You're going to look at when you want to find the pain diff mean, you're going to take the sum of all those things and divide it by a sample. So you're going to take the mean of the pain diff and see how that is, right? So to set up the hypothesis for this, by the way, it looks like kind of like the following. To set up the hypothesis, it's like the following. The mean difference is 0 versus it's not 0. Right, it's a two-sided task we're doing. I'm going to look to see if it's even appropriate to use a t-test here, because if it's not, then I should probably not use this. So I'm going to do a box plot here. You can see that it looks something like this. There's a bit of an issue here. There's several issues. The first issue is that you have a very obvious lower outlier, where somebody had a drug therapy where it was clear that drug B was a lot more potent than drug A, because it's largely negative. That's the one problem. But the other problem is that you can see that the median is closer to Q1 than it is to Q3. It's not actually sitting in the center of the distribution. You also have a long right tail. So it's a bit funny, because if you didn't look at this dot here, you would think it was right skew because it's closer to Q1 and it has a long right tail. But then it also has this really strange outlier in the bottom. So let's look at the QQ. Let's look at the QQ plot to see what we're working with here. Yeah, it looks like this. It's not even the worst of the line, but this lower outlier here is just so low that it's, we should explore what we get when we use another test. So in the lectures, Ken has a package, and I hope I didn't. Yeah. You need to download a couple of things. So please check, guys, because the worst thing that can happen is you haven't figured this out before the test. Right, so here's what you have to do. You need to install DevTools. That's in CRAN. However, the reason why you need to install DevTools is because this package SMMR is actually not in DevTools, guys. Sorry, it's not in CRAN. His package is in his GitHub, right? So his package is in GitHub. And so you need DevTools to be able to use the install _ GitHub to find his package, right? So you cannot actually, like I said, you cannot install his package SMMR from CRAN. It's not there, it's in GitHub. So if any of you if any of your friends don't check the lectures and then try to use library of SM, just to say install that package as SMMR, it's not going to work, right? So please direct them that you have to first install dev tools to use the install_GitHub function to get his package, because it's not in crayon. Okay, so I am going to state that it's doing a binomial test, right? It's doing a sign test. So you can see here that it's not, it's doing a binomial test in some sense implicitly, because to find a p-value, right? Find the p-value, it's actually looking to see how many times an observation is bigger than the median, how many times it's less than the median, basically, right? I want to point out this is not doing a test. I think I made an incorrect statement in the previous lecture where I may have mistakenly said that the sign test is using the mean, but it's not, basically, right? It's using the median. Maybe I'll make a, hopefully people will watch my lecture. It's actually using the median. Right, so when I put in sign test pane, I'm putting in my, because I hadn't used the sign test in a while that I forgot. So I should probably, hopefully people will actually, so this is a sample median. I'm gonna change this here. Yeah, it's the median. It's the median different from 0. So we're not looking at the mean, we're looking at the median here. So I gotta formally amend this on the videos so people don't internalize the wrong thing. So just to be clear, for those who are watching it later on, it is the median, not the mean. We're looking at the sample median, guys. I apologize for my incorrect statement. I actually did not recall because I hadn't used the sign test in a year, and also I haven't had a copy yet. Those two things together and maybe make it into an incorrect statement. So here's the pane data frame that I made before up here. Pane diff is the difference between your two, this difference you have here, right? So pane diff, guys, is not, it's just nothing more than a vector of all the differences. Notice here that I did not actually, it's a vector of all the differences. Oh, it's because I need to attach pane, okay. Notice that pane diff is just nothing more than a vector of the differences. It's not actually a mean, right? So it's saying, give the data frame, give the vector, and then is the median different from 0? If there is really no difference between different things, you should probably expect, I guess, you should expect half above 0 and half below 0 if there's no actual real difference in the pane, right? So there should be half above 0 and half below 0. That's what you should expect. If the median is kind of actually 0, right? So now I'm looking at, I just had difference of 0. So maybe I could put a formal task, right? So I'm thinking that, so if I'm just going to take a mean of the pane diff to get a thing. So mean of pane diff is negative, right? So I'm going to change the test a bit to the following. The mean of the pane diff is negative. So I'm going to assume that the test is the following: less than 0, right? So less than 0 versus bigger than 0, right? So I should use my stylus pen this morning, right? So because the mean is less than 0, I'm going to assume that, for instance, the treatment B maybe work better than A. I don't know, right? So if let's suppose, let me see what it is. Is it pain regulation? I want to see what it is. Actually, let me just double check something. Let's see if it's pain. Yeah, reducing pain basically, right? So, yeah, number of hours of pain relief. So you can see that it's actually negative. So you can see that it's negative, and all I did was take the difference of A minus B, right? So drug A minus drug B. Because it's actually negative, what it's insinuating is that drug B was better because on average they have more hours of pain relief from drug B. Right, so I'm going to assume that the difference between drug A and drug B is less than 0, right? So if you know, which is mu A minus mu B, right, is equal to 0, minus versus the following, basically, that maybe drug B worked better than drug A, right? So if there's actually no difference, you should expect the median should be 0. Like half the people are, half of the drug difference, the difference in the drug should be less than 0, half should be bigger than 0, saying that half the time drug A was better, half the time drug B was better, right? But you can see here from the task, what we get is that none are above 0, not 3 or below, meaning that 9 times out of the 12 times, drug B was better and 3 times drug A was better. But now we can see this is actually significant, right? So if we run this again, we're doing the lower task. We're looking at the lower test here. So we're looking at lower, right? Really, because we're doing a two-sided, we're looking at lower here because we're looking at a actually one-sided test, right? So the p-value is equal to 0.072. Is this significant, guys? What do you think? Is this a significant task for the median? What do you guys think here? You put it in the chat. Is this significant? This is actually bigger than 0.05. Yeah, so it would suggest that it's not actually significant in reducing pain because it's bigger than 0.05. Now, what if I was doing a two-sided test? What would the p-value be instead of 0.07? What would you guys say the p-value would be instead? This is important how to read this. If it was a two-sided test, what would the p-value be instead? It would be 0.14 exactly. And in fact, what I have here is not equal to. So as I said the test here, the p-value would actually be 0.145, but I wanted to test you guys. So in my thing here, the p-value is actually 0.07 because I specified a less than, but in here it's actually, in the way I've set the question up here, where I said not equal to 0, it's actually 0.14. So please make sure you're reading these things carefully. If it was a two-sided test, and I think Ken has an example here in one of his things, you would notice that it would actually be, if your test was greater than, you'd use the greater than thing, right? So it depends on what your test happens to actually be, right? So it depends on the direction of your task that would change the p-value, right? I just want to check here for a second. So in the example he has you can see that the p-value is dependent on, the p-value you use depends on the direction of your task. Because here, for instance, he was looking at greater than, so that's why he was using the upper. But here I specified less than, so I'm using the lower, right? And in this one here, I'm using not equal to. So that's why it's 0.14 here, but in what I have here, when I have less than, it would be 0.072. Just want to make sure that's clear for you guys. Again, I want to point out I'm looking at the median. I think I said in the previous tutorial, because I was just so tired out of it, that was the mean, but it is not. So this sign test is based on the median, it's not based on the mean. And in fact, all the tests after the t-test are based on the median once you've realized that your mean is not a good measure of the center, right? So it turns out that the test is still not significant, even for even using the median test. So it appears, because this is probably because the data set is so small. You literally have 12 observations. That's too low to make a conclusion anyways. But it appears that we don't have a difference in the pain regulation between drug A and drug B. Now, obviously, if we increase our sample size, we might get something different. Right now, did you guys hear about the moods test yet, out of curiosity? Yes or no? Maybe not. Okay, so that's good. I don't really have time to talk about the moods test, but I did make you guys some kind of notes here. Right, so I made you guys a little note here. I even did the median test for you guys. I believe this one is based on, so I think that this one is based on categorical things. Okay, so you're doing the median test today, John. So please don't miss lecture, that's today. But I realized you guys didn't learn it yet, we won't have time. So I made you guys a little extra aside here called the moods test. And I even did the median test for you guys here. This is based on, I believe it's based on, let me just double check, categorical things. Let's just check. Yeah, you can see that it's categorical. So the moods and median test, this is when you have clearly categorical data. I believe the sign test for things that are actually continuous. I made a little thing for you guys here. You can see that I'm even comparing with the chi-square test. You can't use the chi-square test if for certain, sometimes you cannot use the chi-square test, and he'll tell you this in class. If you have small cell counts, so there has to be something else basically, which ends up being the median test, gives you a better approximation when you have small sample sizes. I'll talk about this today. after you learn this in lecture, then it might be kind of cool to go back and look at this tutorial worksheet here that I left you from line 143 onwards. But again, just to be clear, the sign test is using the median. I want to make this clear for those who are watching later on, especially those from the first tutorial session, and let them know that I made this change. So it's actually median, that I made a mistake because I hadn't worked with the sign test for a while and I was a bit tired. But yeah, I just want to make this correction known on YouTube because I don't want people to internalize the wrong thing. But I left this little note here for you guys to continue for yourselves after you learn the lecture today. So after the lecture, go back and look at the moods test and the median test. Try it out for yourself. It's for categorical data, which is different from continuous. You can see in the sign test here, we're working with continuous data. So look at the pane diff, you can see that it's numerical, whereas this one is obviously not, right? That's the distinction there. So I'm gonna stop. Have a great test, guys. Good luck, and I'm sure you guys are gonna smash it. And I'll see you guys, I guess, next week is reading week, so probably 2 weeks from now. I'm gonna post to you guys today so you guys can go back and watch and practice after lecture. I think so. So the way I would actually probably work on, so I think it might be in person after reading week. And I thought about this because obviously before how this used to work when I was teaching the course in person was that I would walk around and I would look to see people's work when they're on their computer stations, but I can't do that. So I might have to stand in front of the class, put the projector on and teach from the front. And then if people have questions as I'm going through manipulations, they can ask me and I'll interface with them from the front. But yeah, I think it's supposed to be in person, but I probably won't be walking around because that would be a public health problem, right? I'll probably still teach in the front with my mask on. But yeah, probably we'll know more about that in a couple of weeks if our numbers are clearly actually going down.